Next, we want to look at different types of rocks. Now, I've already said that a rock is an aggregate of minerals or a combination of minerals. So it's sort of like how a compound is a combination of elements. Well, a rock is an aggregate of minerals, and specifically, it's a physical mixture. And there are generally three categories of rock, and the three different categories are determined by how the rocks were formed. So the first kind of rock is what's called an igneous rock, and that's formed from cooling and crystallization of magma or lava. So we talked in the previous lecture about how crystals can form out of magma when it cools, and those crystals are what we call igneous rocks. Now, another kind of rock is what's called sedimentary rocks, and sedimentary rocks are formed from pre-existing rocks that are subjected to weathering and erosion. And we'll talk about what those are shortly. And then finally, the third class of rock is what's called metamorphic, and these are also formed from pre-existing rock, but they're rocks that have been transformed by heat, by pressure, or by chemical fluids. So let's look at igneous rocks. Igneous rocks are formed from the cooling and crystallization of magma and lava. Now, magma is the molten rock that forms inside the earth, and lava is molten rock that is erupted at the Earth's surface. So that's the difference between magma and lava. But each of these can, as they cool down, have things crystallize out and become igneous rocks. Okay, we want to look at the role of heat in the formation of igneous rocks. Now, the first thing that we want to note is that temperature increases within the Earth's upper crust. That is, if you were to imagine digging a well, very, very deep well, as you descended deeper into the Earth, it would get warmer and warmer. And so we call that warming a geothermal gradient. And that gradient is an average of 30 degrees per kilometer. In other words, if you go down a kilometer into the Earth's crust, you'll see that the temperature raises about 30 degrees Celsius. If you go down another kilometer, you would find that the temperature has gone up by another 30 degrees. Now, rocks in the lower crust and in the upper mantle, those rocks tend to be near their melting point. Any additional heat, say from rocks descending into the mantle or rising heat from the mantle, they can induce melting. And so we find that heat does have an effect, but actually it's a minor player in this process. Now, another thing that impacts this is pressure. And just like if you go into the ocean and you go deeper and deeper into the ocean, you find that the pressure increases. The same thing happens as you go deeper into the Earth's crust or deeper into the lower layers of the Earth, that the deeper you go, the higher the pressure. Now, if you have reduced pressures, that's going to lower the melting temperature of the rock. When confining pressures drop, decompression melting can occur. In other words, you might have some rock underneath the Earth's crust that's not melted. It's a very high temperature because the high pressures there mean that you have to have a higher temperature to melt it. But if the pressure is released, then the melting point gets lowered, and then that rock can suddenly melt. That's what decompression melting is. Now, another thing that can have an influence in the generation of magma is the presence of fluids. And mainly when we're talking about this, we're talking about water. And basically, if there's water embedded in the rocks, that can cause them to melt at lower temperatures. An analogy to this, if we add salt to water, that can cause ice to melt at a lower temperature. That's why, for example, when it snows, they put salt on the road because they want the ice on the road to melt. And by lowering the temperature necessary for ice to melt, you can clear the roads more quickly. So let's ask a question just to check our understanding of this. So the question that we have is, even though the temperature at depth is hotter than a rock's melting point, the rock at that depth is solid. Why is that? In other words, a rock has a certain temperature. If you go above that temperature, it's going to melt. And as you go down towards the center of the Earth, it gets hotter and hotter. And yet there are large areas where you have solid rock at temperatures higher than what they would need to melt under normal circumstances. So how is it possible that they're still solid? Well, obviously they're not what we would call normal circumstances. So what's different? And the basic idea is that they are under enormous pressure from the rock above. Now, why is that important? The increased pressure prevents their melting. That's what we just talked about. The higher pressure changes the melting point. And the temperature would have to be even higher to counteract the increase in pressure. All of these are true. So actually the answer to this is D, all of the above. Now the next point that we want to make is that the melting of a rock into magma occurs over a broad temperature range. And that's because the magma will melt in stages. So remember that a rock is a combination of different minerals. And so maybe some minerals will melt at a lower temperature than other minerals. And so a rock that's composed of different minerals will melt as one mineral melts, and then as the other mineral melts at a higher temperature, and so on. And when that happens, minerals with low melting points, those with high silica contents, if you recall, those are going to be the first to melt. And that sort of partial melting results in a silica-enriched magma. So you have the sort of the liquid magma which has this enhanced silica that is melted in it. And of course, the reverse of that process is true. As the magma cools, minerals will crystallize systematically based on their melting points. So minerals with different melting points will crystallize at different temperatures, just as they melt at different temperatures. And minerals with high melting points, those have low silica content, they're going to be the first to crystallize. The process of crystallization acts to enrich the remaining magma with silica. And minerals with low melting points, those that have a high silica content, they're going to be left in the melt. Now, the mineral makeup of igneous rocks is dependent on the chemical composition of the magma from which it crystallizes. And so there's three basic types of magma. There's basaltic, andesitic, and granitic. And igneous rocks are further classified according to where they are formed. Rocks formed from magma that crystallizes at depth are classified as intrusive or plutonic rocks, and rocks that are formed from lava at the surface are classified as extrusive or volcanic rocks. One way that might help you remember this, you might remember from Roman mythology that Pluto was the god of the underworld. So the plutonic rocks are the ones that form underneath, down in the magma. Whereas volcanic rocks are rocks that are formed at the surface. They're the ones that are from lava, which is emitted at the surface that cools down on the surface. Now, it turns out that there are three different kinds of volcanoes. There's what's called a shield volcano, a cinder cone, and a composite volcano. I'm not going to go into all the details of what makes something a shield volcano versus a cinder cone or versus a composite volcano, but there are differences in structures, and there are differences in how they're formed, and there are differences in how they erupt. And so just know that there are different ways that different types of volcanoes are classified, and these are the three main kinds. Now, just reminding you what we said earlier, igneous rocks that cool beneath or below the Earth's surface are called plutonic, and granite is the most common kind of plutonic rock. So granite is, of course, a very famous rock. Most people are familiar with granite. They know what it looks like and feels like. If you have underneath large expanses of plutonic rock, those are called batholiths. And that just means it's a very large area that is composed of some kind of igneous rock. Now, the next classification of rock is what are called sedimentary rocks. And so sedimentary rocks are rocks that form in a process of 4 stages. There's weathering, erosion, deposition, and then finally sedimentation. And we'll talk about what these mean. So weathering is the physical breakdown and chemical alteration of a rock at the Earth's surface. And there's 2 basic types. There's mechanical weathering and there's chemical weathering. Now, mechanical weathering is a breaking or disintegration of rocks into smaller pieces. Let me give you an example of a kind of mechanical weathering. Imagine that you have a rock that has some cracks or pores in it, and water gets into these rocks and pores and then freezes. As the water freezes, water is a very special material in that when it freezes, it actually expands. Most things contract when they freeze, but water actually expands. And so if water gets deep into these rocks and the rock freezes, as the water expands, it can exert an outward pressure and cause the rock to crack into or fracture. And so that can create a kind of breaking down of the rock. That would be a mechanical process where the water expanding is physically breaking down the rock. So that's a kind of mechanical weathering. Chemical weathering is where you have chemical decomposition and transformation of rock into one or more compounds. So maybe some of the rock is being dissolved away, or maybe chemicals are being added to change its composition in some way. These are the kinds of things that can happen with chemical weathering. So here are some examples. I was just talking about a process called frost wedging. That's the alternate freezing and thawing of water in fractures and cracks, and that can cause the rock to sort of break apart. Basically just the thermal expansion of the rock itself. If the rock heats up, it's going to tend to expand. As it cools down, it's going to contract. And just over time, if this process is repeated over and over, the rock can get weakened by this process and break into pieces. Biological activity can cause rocks to disintegration. For example, lichens could form on a rock and cause it to become, broken down. Now, another kind of thing that's important is chemical weathering, and that's actually the main producer of sediment. And it breaks down rock components and their internal structures, and the most important agent involved in this is water. Now, another way that rocks can be broken down is through erosion, and that involves the physical removal of material by mobile agents such as water, wind, ice, gravity. And so you could imagine, for example, a mountain range where wind is blowing dust, and as the dust blows across the mountain range, it's wearing it away like sandpaper. That's the kind of thing that we could be talking about. And so water, wind, ice, gravity, these are all things that can contribute to erosion. And of course, erosion doesn't really occur in place. It involves some kind of movement. And then once rock has been broken down into pieces, the last stage is deposition. And that's when the eroded particles come to rest. And so the larger particles are the first ones to be deposited, and the smaller particles are able to remain with the flow. And in this way, sediments get sorted according to what size as they are deposited. And so you can see the picture here. You have well-sorted sediments and you have poorly sorted sediments. You can see sort of the contrast in size here of the parts of the sediments. During sedimentation, sediment particles are deposited horizontally, layer by layer. And as the deposited sediment accumulates, it changes into sedimentary rock. So all of these particles get fused back together and form a sedimentary rock. And this process is actually called lithification, and it occurs in 2 different steps. You have compaction and cementation. And cementation, it makes you think about cement. Think about cement because that's going to be important to understanding how it works. But basically the idea is this. You have all these particles layer upon layer. And so you have a layer of sedimentary rock, and then over time more sediment is deposited on top of it. And then over time more sediment is deposited. And so the layers that are deeper, they're experiencing lots and lots of pressure. And so that pressure pushes those particles together. That's called compaction. So here's what happens. The first stage is you have this compaction, and then that process, as these things are pressed together, water is squeezed out from the gaps in between the sediments. And the water that's remaining often contains lots of compounds like silica and calcium carbonate and iron oxide. And these compounds can precipitate out of solution and fill up the gaps with mineral matter. And this kind of material sort of glues the particles together and acts as a cementing agent. So just to sort of recap, we have compaction, where the weight of overlying material presses down upon deeper layers. And we have cementation, where compaction releases the pore water, which is rich in dissolved minerals. And this mineralized pore water acts as kind of a glue to cement these particles together. Now we can further classify sedimentary rocks into clastic rocks, which are transported sediment particles, bits and pieces of weathered rock. Examples of this include shale, sandstone, conglomerate. And then there are what are called chemical rocks, where the sediments were once in a solution. And we have travertine, halite, limestone, etc. And so basically, those are the different kinds of sedimentary rocks, those that came out of solution and those that were, rocks that were broken up into little pieces and weathered together. And so clastic sedimentary rocks are classified by their particle size. And so we have shale, which consists of mud-sized particles in thin layers. And this is the most common type of sedimentary rock. Then there's what's called sandstone, which has sand-sized particles. And quartz is a predominant mineral of that. And then we have conglomerates, which have particles that are greater than 2 millimeters in diameter. And examples of this are the kinds of things like rounded gravels. Here we have an example of limestone. It's the most abundant chemical rock. It's composed chiefly of the mineral calcite. Marine biochemical limestones form as coral reefs and other things, but this is an example of limestone. Now, another kind of chemical sedimentary rock is what's called evaporites. Look at that, evapor, looks like evaporation. And that's exactly what an evaporite is. It's a rock that comes from water evaporating out and leaving things behind. So evaporation triggers the deposition of chemical precipitates. Examples include rock salt and the rock gypsum. Now, earlier we said that most rocks are formed from minerals that are organic, but one of the main differences is coal, which coal is different from other rocks because it's based on organic material. And so the stages in coal formation in order are you have some kind of plant material, and that plant material, as it dies and decays, it gets compacted into something called peat. And then over time, you add pressure and heat and more pressure and heat. And the structure of that material actually changes and forms into coal. So let's look at one of our little quizzes here. The most characteristic feature of sedimentary rock is A, that they contain fossils, B, the lithification and cementation of sediments, C, the layered sequence of strata, and D, the fusing of unconsolidated sediments into solid rock. Well, the answer is actually going to be C, the layered sequence of strata. Remember what we talked about. So the sediment is deposited, and then the process brings another sediment on top, another layer of sediment on top, and then layer after layer, they get the lower layers get pressed together, and that causes the process of compaction, and then you have cementation coming in later. But it all starts with this layering sequence of strata. Now, the next kind of rock that we want to talk about is what's called metamorphic rocks. And metamorphic rocks are produced from basically all the other kinds of rocks. They're produced from igneous rocks, from sedimentary rocks, and even from other metamorphic rocks. And metamorphism occurs via recrystallization and mechanical deformation. Basically, the idea is this. You have a rock that's formed by one of these processes, and through some mechanism it's transplanted to a location where the temperature and pressure is different, and that change in temperature and pressure can alter the rock, and so there's a metamorphosis from one structure to another structure, hence it's a metamorphic rock. Now, there's two kinds of metamorphism that are involved in this, what are called contact metamorphism and regional metamorphism. And so contact metamorphism is associated, imagine that you have a region of rock and some magma gets forced into this region of rock. And so right around here, near where the magma is, this rock around it can be altered because of that heat. And so you have, this is sort of an example. So this is called contact because the contact of this heat source is altering the rock. The other kind of metamorphism is called regional metamorphism, and that's the alteration by both heat and pressure over an entire region, rather just near a contact between two different rocks, like we talked about in the last slide. Now, metamorphic rock is defined by its appearance and by its mineral content. And there's two different groups of metamorphic rock. There are what are called foliated rocks, and those are layered in sheets. And you have the non-foliated types of metamorphic rocks which aren't in layers. Here we can see some examples of foliated metamorphic rocks. Those are rocks, and you can kind of see that there's like some different sheets, different layers in them, and so those are called foliated. And here you see some examples like marble that are not foliated. There's no like layering of sheets like in the previous slide. And finally, we want to talk about the rock cycle, which basically it's a process where molten rock rises from the depths of the earth, it cools, and it solidifies. And eventually it returns and becomes magma again. And so you sort of have this cycle over and over and over again.